Thank you. Okay, so we had a conference about platform engineering. I'm an application developer. This is not a talk about platform engineering, so I'm really happy to see so many people. What I'm going to tell you about is our journey in Lunar, building an event-sourced banking core, modern banking core, built on top of a cloud-native platform. And of course, you need some AI in your talk these days, so that's why I rendered an image of a cloud-native bank. Okay, so let's get into it. First, a little bit about me and Lunar. I joined Lunar back in 2016, so I've nearly been there from the beginning. So I've been on the complete journey from a Rails monolith to our current event-driven microservice architecture on top of Kubernetes. Right now, I'm a tech lead in the squad responsible for domestic clearing integrations and account transfers. I've been in the game since around 2004, so I'm old enough to actually have done J2EE. Lunar, we were founded in 2015. We think of ourselves as a technology company running a bank, and that's what gives us the edge above the other banks in the business. In 2019, we received our banking license, and we went live on that as a real bank in 2020. We have around 750,000 customers across the Nordics. On the tech side, we've been cloud native from day one. We went live on Kubernetes in 2017, so pretty early compared to others. We've been using event sourcing since 2019. Right now we have around 300 application services in our Kubernetes cluster, and a bit less than 100 services are using event sourcing. So when we got that license, that's why it was in bold, that's sort of the starting point for this talk. When we got that license, we had to ask ourselves, how are we going to build this bank? Before that, we were running on top of another bank, so all the regulation being compliant was sort of their business. Now we had to do it ourselves. So how would we build this in order to support being a compliant bank? So the answer we came up with is, well, we're dealing with people's money. So of course we want our bank to be absolutely correct. No surprise, we all want our systems to be correct. But the really interesting part is what happens when it's no longer behaving correctly. And that is going to happen. Users behave in unexpected ways. Integration partners behave in unexpected ways. Weird coincidences happen in production. Then how do your platform behave? And what we wanted first and foremost was explainability. We wanted always to be able to understand and explain what happened in the system. So we should never end up in a situation where I have no idea what happened with this customer's money. We always wanted to be able to say, hey, something went wrong, but we know what went wrong. Because if we can explain it, then we can also fix it. So that's what led us to event sourcing. So what is event sourcing? Basically, it's a persistence model where instead of persisting the state of the system, we persist all the changes happening to a system in an immutable sequence of events. So, how many in here have built applications in production using event sourcing? My colleagues and some other. Okay, good. So at least a bit of knowledge in the room. So what are good examples of event source systems? Well, I guess all of you are using an event source system on a daily basis, namely Git. Git is event sourced. A commit, each commit are the events, and you get to the state of the code base at a certain time by applying all the commits in order. But if you look up in a textbook on event sourcing, or these days you ask ChatGPT, give me an example of an event source system, it comes up with, on page 1, financial transaction system or banking application. So no surprise that we also arrived at that conclusion. But what comes after page 1? That's what I'm going to talk about. So let's start out with a very simple example, and I'm going to elaborate on that during the talk. The account, an event-sourced account. At some point in time, the account is opened. We have an event, account opened. A bit later, some money are deposited, and a bit later again, money are withdrawn. So the event stream captures all the important business events happening on this account. So in the event source system, we represent everything as this stream of events. What about the state? What if we have to decide on doing some action, user wants to withdraw money? How do we actually validate such a command? Well, we can always calculate the state. We don't need to have it persisted anywhere. So we calculate it by applying the events in order, just like in Git. So at this event, the balance is 0. After the event number 2, the balance is 100, and down there it's 50. So the state in functional programming terms is a fold left from the 0 state and applying all the events in order. Okay, so pretty simple. That's page 1 example, but how do you actually then implement an application using that? So that's what I'm going to talk about first. How did we choose to implement this? First, how do you actually write to a stream? How do you do that in a consistent manner? So let's say the account is, at this point, it has been opened and the customer has put some money into it. Now, there's a command coming in to withdraw some more money. How do we actually handle that command and process it? Well, we just have to first get to the state of the account by what we call projecting the stream into the state. The state is the account is open, balance 100. Then we validate the command against this state. The account is open, there's enough funds on the account. And then we write the new event to the event stream. So this is event number 1, 2, and 3. But what happens if somebody else came in between? So after we read our events, a competing write actually succeeded, writing event number 3. So now this is no longer consistent. What we evaluated the command against is no longer the true picture of the world. So in this case, this write must fail. That's how we uphold consistency in the event-sourced world. This is basically what you have to implement if you do event sourcing. Sounds easy, right? How would you do that? Well, back in 2019, when we started on this, we had to decide how we're going to do this. So you can either build it yourself. You have complete control. You're on your own. And you have a maintenance burden going forward. Or you could buy, evaluate what's available in the market, evaluate it, cost, complexity, evaluate it against your technology stack and your platform, see if there's a good match. Back in 2019, we were already established as a Go shop. And in the Go world, there wasn't really any good possibilities of picking something from a shelf. We looked at Event Store DB, Greg Young's product. At that time, it didn't really have a good cloud offering. So we decided to go with the build. So we have built a Lunar Go library. It's still closed source. Maybe at some point it will be open source. I hope so. It's using really boring technology beneath it for storage. It's using Postgres. And that was a conscious choice, just choosing something really simple that we were already using and had good experience with. And it enabled us to actually just use a simple SQL unique constraint in order to give this consistency guarantee. So just by numbering all the events, remember, we want to write event 3, but somebody had already done that, and then the write fails. If I had to do this again, I'm pretty sure I would do the same. This library has served us well. It's running in a lot of applications, and there's really only one thing which we are struggling a bit with, and I'll get back to that later. So, after building the library, you of course run into some challenges. The first challenge we ran into was that of the long and long-lived event stream. Some stats. Right now, in the Danish setup, we have around 800,000 account event streams. Some of them have more than 50,000 events. So if you're using your account a lot, there'll be a lot of events on the stream. A lot of them have been running for more than 3 years. Thankfully, we have customers who are very happy about us, so they stay for a long time. And during that period of time, our understanding of the banking domain itself has evolved a lot. So of course, we didn't get it right in the beginning, the events we wrote to the account. So events have also evolved. So how do you actually manage that? Well, bullet number 2, 50,000 events on some streams. What happens when you're going to load that amount of events into memory whenever you have to decide on something? This happens. This is from June 2020, so a bit less than half a year after we went live. The span is a month, so over a month, and the orange part is the 95 percentile of load times of loading the account. That's a kind of graph you don't want to see, right? Extrapolating this, we knew we had not very much time before this would not work anymore. So what do? Well, you introduce snapshotting. So what is snapshotting? Well, it's once in a while you store the current state of the account. So after X number of events, in this case 10, you do a snapshot of the account, and then when a command comes in, what you have to do is then just start by loading the snapshot and then apply additional events on top of that. So instead of loading the complete event stream, you just load the snapshot and at most X events. And then you proceed as before, validate and write new event. So we implemented that over the summer in 2020, people going on vacation, and it was pretty hectic. But we managed, and after the summer holiday, when we got it into production, this was then the picture. Load times reduced from fluctuating heavily, depending on how many events in the event stream, to very consistent load times, and actually pretty fast. I don't know if you can see it, but 20 milliseconds, that's here. And that's been the picture since. Okay, some takeaways about snapshotting. This is an absolute must-have when doing event sourcing if you have long event streams. You need that at some point. You have to be able to do it independently of writing new events. So it's not okay to do it as part of writing the new event. Then you'll impact the write side, and you don't want your write side to be impacted by you having to do some snapshotting. There's one challenge. Evolving the state now becomes a problem, because what if you need to change something in the state you store in the snapshot? Then all the snapshots need to be invalidated, and the next time you need to load the account, you have to load all the events. So you need some mechanism at some point to warm up snapshots on version bumps. We haven't actually solved that. We're running without that. So fortunately, we haven't had to change the state of the account for years now. It's just running. But when we do that, we actually take a hit. So if your card transaction times out and you're a Lunar customer, it could be because we were actually invalidating the snapshot at that point. Okay, so another problem with the long-running streams is unbounded state. So here's a naive picture of what the account state could look like. Some properties about when the account was created, the balance on the account, and then some maps down here. So reservations, a map of all reservations that have happened on the account in order to be able to do this idempotently. When you reserve some money, you don't want to do it twice. So in order to do this idempotency check, we have a map in here with all the IDs. That might be okay for some time, at least, and on accounts with not that much activity. Right now in Lunar, we are launching a product where we'll have hundreds of thousands of transactions on an account each month. This won't scale to that. Then you get unbounded state in, and you have to load this into memory. Kubernetes will kick in and give you OOM kills all the time. So that doesn't work. You have to solve this idempotency differently. Move it out of the projection of the state. And I'll come back to a bit later how you can do that. Okay, so this was a bit about modeling, so the account state. A bit more, how do you model with event sourcing? And again, I'll use a concrete example, how we did in the beginning, modeling a transfer. So to begin with, we actually modeled the transfer on the account. So a certain subset of events on the account stream represented a transfer. So the transfer was initiated, then we reserved some funds on the account. We were already on the account, so that's pretty easy. Then we sent the transfer to the clearing to get it through the domestic clearing. When that succeeds, the transfer cleared event is put on the account. And finally, we turn the reservation into a posting instead. There's some obvious problems here, right? First and foremost, it's all about responsibility. Now this event stream has two responsibilities. It has to keep track of the account, postings and balance, but it's also implementing the transfer, which is very short-lived. So we have two competing concerns here. A transfer implementation that you might want to evolve, but it's now sitting on something which is really long-lived and is harder to change. So you have all these events sitting there that you have to be able to load. Evolving the implementations are difficult independently. And again, idempotency. Now the account also have to guarantee idempotency of transfers. So what we did pretty quickly was to pull out the transfer to its own short-lived transfer event stream. So now we just have a very short-lived event stream containing these events representing the transfer. And this transfer is then using the account just as a ledger to reserve money and turn it into a posting at some point. This leads to a bit about DDD. Event sourcing loves DDD. Domain-driven design, how many are familiar with that? Oh, great. Yes. Okay, so you know, most of you or some of you know about this. So in domain-driven design, we really want to understand our domain and use that understanding in our implementation from the very lowest level to the top, using the language of the domain to express also our code. This is an example of a practice in DDD, event storming, where we try to model the processes, the things happening in the domain using stickers, sort of a game. you can play. Event sourcing is really well suited for that, because what we do in event sourcing is precisely to store these things happening in the domain. So right here in the middle, we actually have the events from the credit transfer event stream represented as in this event storming session. So we try to use DDD heavily in Lunar. We use it to identify system boundaries, identify aggregates and the events on the event streams. We use it on a daily basis. As we all know, one of the two hardest parts in computer science is naming, and that becomes even more important in event sourcing. Those names of the events really have to express what happened in the domain. Just by reading the event stream, you should be able to see what happened here. Key takeaways about modeling. You should define your event streams around a single responsibility. Really, really important. Single actions and workflows should be separate event streams. At some point, you need to have some kind of support for event evolution. When your knowledge of the domain evolves, you also need to be able to evolve your events. Remember, it's an immutable sequence of events. So in principle, you're not allowed to update events. But somehow you need to be able to do that anyway. We do that in memory. So when we load the events from the event store, we have a mechanism for automatically upgrading events. And I strongly encourage you to embrace DDD if doing event sourcing. Use it to identify boundaries and modeling streams, and use it on a daily basis for event naming. Okay, let me just check time. Oh, I need to speed up. Okay, event subscriptions and side effects. The next challenge, because right now, until now, we have talked about the center of event sourcing, the persistence layer. But how do you actually build an application that has an impact in the environment? You just don't need to store stuff. You also need to do stuff. What about read models, side effects? So the answer to that is event subscriptions. So it's very similar to pops up messaging pattern. Producer produces events in this case, and some consumers subscribe to these events and can take actions. It also comes with some guarantees, at least once guarantee on delivery. A handler should be guaranteed to get all the events at some point. And furthermore, it must be in order, since this is an ordered sequence, and getting event 1 before event 2 can be really important for the handler. This is where we're struggling still a bit. The last part, in order, that's difficult. So if you think about Kafka, that's actually what Kafka have solved, and Kafka is not an easy piece of technology. Just getting at least once guarantee is sort of easy. We're using an outbox pattern, so when writing the events, we also write to an outbox, and then consumers are handed the events from there. But getting the order, that's the difficult part. So what are we using this for? We're using it for internal read models, for example, idempotency. So instead of having the idempotency in the state of the account, you can pull it out to a read model in a SQL back table and base your idempotency on that instead. We use it for external read models, the query side of CQRS. So the event store is the write side. The read side, you can do any kind of external model, or place it in SQL or wherever in a document store for the read APIs. We use it to execute commands both inside and outside the domain, so having an effect in an external system. We publish integration events. The Lunar architecture is an event-driven microservice architecture, so all business events happening in some domain is propagated as integration events for other services to consume. And we use it for process orchestration, think sagas. The credit transfer flow is actually a little saga where we're also using this mechanism. So let me see what. 5 minutes? 10 minutes. Okay, great. So let's see this in practice. Again, the credit transfer. We have the short-lived credit transfer event stream down here and the account ledger event stream up there. When the command comes in, the transfer initiated event is written on this stream. Then a consumer consumes that event, turns it into a command to reserve funds on the account, which in turn produces a funds reserved event on the account event stream. When the command completes, a new event is written down here. Now we succeeded in reserving the funds. Guess what? A new consumer comes in, handles this event, and sends the credit transfer to the external clearing. When that succeeds, hopefully, or at least we get an ACK, yeah, this is going to go through. We store a transfer executed event, and that then in turn is consumed and turned into a command to capture the funds on the account, which produces the funds withdrawn event, and we can then finally mark the transfer as posted on the account. That's in principle how we do transfers. Key takeaways. Again, just like for snapshots, the consumers must be independent of writing new events. Whatever side effect is going on in that consumer can be very time consuming. You don't want to have that to happen on the right side. So it must be done in another process. Item potency is of course really, really important. We have at least once delivery. So if you get the event again, the action you take should be item potent. That can be difficult if you have old integration partners. We have a certain integration partner that has an API which is far from item potent, causing a bit of a headache once in a while. You have to embrace eventual consistency. Since the actions are independent of the write, at some point there'll be inconsistencies. If also an error happens in the consumer and you're not getting your read model updated, then the write side, the event store and the read model is no longer consistent. So you have to have ways to handle that. Event replay must be supported. You introduce a new event read model, sorry. Then you need means to actually replay all the events and get the read model warmed up before you start using it. And as I said, it's a bit difficult to get right, this guaranteed ordering. Hopefully we'll have it sorted soon. And I'm really happy to discuss this with the other people in the room who maybe have had that challenge. So finally, we're getting to maybe the question you have all wondered about. What has this to do with the cloud native world, and has it actually given us anything? So has being cloud native made implementing all of this easier? Not directly, but it certainly helps. And what helps is the mindset. In Lunar, the cloud native mindset is very much also an agile mindset. It's about continuous improvement, getting things into production fast, doing short feedback loops, trying things out. And that mindset has really helped us also in implementing event sourcing. The tooling, our platform. There's a lot of talks and blog posts about our platform out there that you can go and find. It's really, really awesome. That helps a lot as well. It gives us insight into what is going on inside all of these event sourced services. So Backstage, our homegrown open source build tool, Shuttle, Kubernetes, of course, and then the observability stack, Humio, or log scale, as I suppose you should call it now, Prometheus and Grafana. All that turns it into a platform where we can really go fast. It's really, really fast to get going and try new things. So it helps. Finally, the last slide. So evaluating event sourcing after having done this for 4 years now in production. Does it deliver on the promise of explainability? Yes, it does. It is really a superpower to be able to go in and see these event streams, see, oh, that's what happened. I hadn't thought about that we could get this sequence of events and then something terrible happened. But it's not 100%. You still need, for example, one example, competing rights. If you have 2 actions going on at the same point, then only one of them will succeed and write to the event source. The other one will not. So you have no proof of that except for in the logs maybe. So you still have to have a good logging mechanism to be able to figure out what really happened. It really is, in our perspective, an attractive model. The division between write and read is really, really good. You get some real power from that, but complexity is also higher. And last but not least, don't use it for everything. We did that in the beginning, which was a major mistake. We have, actually the longest event stream we have is something where we are trying to do uniqueness of account numbers using one event stream. That's a pretty long event stream. I think it has 2 million events right now. Don't do that. Okay, only use it if it actually suits the domain. I guess that's about it. In the example with the credit transfer, yeah, but that's, you have 2 different event streams. So credit transfer initiated triggers a handler that then does a command on the account. So
couldn't you end up in a problem where you haven't executed the transfer to some external system and then not be able to write back the event?
Well, yeah, in principle, the account could be closed in between. Yeah, you have reserved the funds, then you execute the transfer, and then for some reason the account is closed.
I guess the question is about the side effects happening before the commit.
Yeah, but the side effects are only happening based on an event. So never do side effects if the event triggering that hasn't been written. So it's sort of a sequence. Maybe let's talk in the break. Yeah. Oh.
Sure. So you said that if you were to do it all over again, you would do it the same way. Nowadays, there are AWS and Azure have immutable ledger database offerings. Have you considered if that could be useful instead of Postgres?
Yeah. We also actually have looked at Event Store, for example. Event Store has a really good cloud offering now. One of the things that it's sort of a beast. So when you put that in Event Store, the idea is that you're writing everything to the same Event Store. So you have